Hello everyone, and welcome to today's video. Today's topic is linear dependence and independence. We'll define them and see a few examples. Let's start with the definition. Pick a set of vectors, v1 through vk. We say that the set of vectors is called linearly dependent. Sometimes I will be a little sloppy and say that the vectors are linearly dependent. If there are constants, C1 through CK in R, not all zero, such that I can write zero, the zero vector, as a linear combination of the vectors V1 through Vk with coefficients not all zero. I want to bring your attention to the last remark in the previous video, in which we saw that at some point we wrote the zero vector as a linear combination of vectors V1 through Vk, and we knew that at least one of the coefficients was non-zero. In other words, the vectors v1 through vk in that example were a linearly dependent set. The counterpart to linear dependence is the definition of linearly independent. So we said that instead, a set of vectors v1 through vk is linearly independent if you cannot write zero as a non-trivial linear combination of the vectors. So in other words, if the only way that you have to write the zero vector is by having that all of the coefficients in your linear combination are also zero. Let's play around with this example and see how these two concepts of linear dependency and independency tie up with what we've been doing so far. Here are two sets, S1 and S2. Both contain three vectors. And we want to determine whether the corresponding sets S1 and S2 are linearly dependent or not. So the way we do that is by using the point of view of linear dependency on something that we've already accustomed to. Linear dependency means that we want to write zero as a linear combination of the vectors in here, possibly using non-zero coefficients. So the possible choices for coefficients to write the zero vector are the same as the solutions to a linear system AX equals 0, where A is the matrix whose columns are the vectors in S1 and in S2. So let's try and do that. I'll work out S1 on this side of the page and S2 on this side of the page. So for S1, the linear system that we would like to solve is that with coefficients 1, 1, 1, 1, 2, 1, 0, 0, 1, and then we would like to know if there's any solution when the vector of constants is a column of zeros, like this. Let's do this, and then we'll move back to S2. The way to solve this system is the usual one. We'll use Gaussian elimination, which means that in the second row, I'll replace it with itself minus the first. So I'll get 0, 1, 0, 0. And the third row will be itself minus the first. 0, 0, 1, 0. Gaussian elimination is not quite completed. We still have to get rid of the extra non-pivot entry in the second column. And we can do that by replacing the first row by itself minus the second, if we subtract the second row. So we get 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. This is now in reduced row echelon form. And in fact, if you read through the meaning of this matrix, this is telling you that x1 must be 0, x2 must be 0, and x3 must be 0. We'll interpret this result in a second, but let's take a step back and have a look at what happens in the case of S2. we have a similar matrix. We want to solve a problem. This time, this third column is slightly different, but we still want to solve a linear system whose constant terms are 0. So let's do it again. I'm not going to write the steps. 1, 1, 3, 0. I'll subtract the first from the second, so I get 0, 1, 1, 0, and I'll subtract the first from the third, 0, 0, 0, 0. Something different is starting to happen. We see a row of zeros, which tells us that the behavior will be slightly different. Let's finish our Gaussian elimination. To do that, I need to subtract the second row from the first. Now, if we look at this equation here, we see that x3 is going to be a free variable. And the other two equations are x1 is equal to -2 x3, and x2 is equal to minus x3. So for example, in other words, well, let's put it like this. Solutions to this linear system will have the following form. X will be a multiple of x3 by this vector, -2, 1, and this should be a 1. So there's infinitely many solutions, and they all have this form. Let's wrap this up. What does this mean? In this case, there is no way, so in case S1, the only way that we can write the 0 vector as a linear combination of some columns, of the columns of A, is that the coefficients for the linear combinations are all 0. In this case here, we may write the 0 vector as a linear combination with non-zero coefficients, -2, -1, and 1, of the columns that we started with. In other words, S1 is a linearly independent set, but S2 is linearly dependent. If we wanted to be more explicit about how to write the 0 vector in the case of S2, we could do the following. I can take the columns of S2, 1, 1, 1, and then it's 1, 2, 1, and 3, 4, 3. I want to write 0 with these, and one possible choice I have is given by my solution. I put in the coefficients given in one of these solutions to the linear system, and if you check this, you'll see that you get exactly the 0 vector on this side. So that gives us the linear dependence. The upshot here is that to check whether a set of vectors is linearly dependent, you want to set up the corresponding linear system whose associated matrix has as columns the vectors that you started with. If that corresponding linear system with a 0 term has only the 0 solution, the set was linearly independent. If there's some non-zero solution, then the set was linearly dependent. Here's another one of the big statements, the big theorem that relate this new concept we have of linear independency to concepts that we've already had. So let's just read through these conditions, and maybe let's try to convince ourselves that they are indeed equivalent to one another. We pick a matrix, m by n. saying that the columns of A are linearly independent is the same as saying that the only way that I can write 0 as a linear combination of the columns of A is using 0 coefficients. In other words, the linear system AX equals 0 only has 0 as a solution. Having 0 as a solution means that you have no free variables. In other words, the nullity must be 0, because the nullity of A is the number of free variables it has. But the nullity is also the difference between the rank of the matrix and the number of columns of the matrix itself, which is equal to n in this case. So if the nullity is 0, then the rank must be the same as the number of columns. However, having the rank equal to the number of columns means that there's many distinct pivot columns, and every one of them has to be an entry in a different position. So the columns of our the columns of our matrix A in the reduced row echelon form, they need to be all distinct standard vectors for the rank of A to be equal to n. Take a second to think about it and maybe try to draw a matrix down. You'll see that there's no other way that this could happen. Another thing that the rank being n forces is that there must be a pivot in every column. The rank is the number of pivots. If it's equal to the number of columns, then there must be one in every column. Maybe something that is not surprising at this point is that, but we'll comment more about it later, linearly independence of the columns is equivalent to this last condition here. When the columns of A are linearly independent, then the linear system AX equals B with any B chosen in Rm has at most one solution. So that's something that we haven't discussed in examples quite yet, but it's something very important related to linearly independence. When you have linearly independent columns, then you have at most one solution for any linear system. Moving on, we saw something important show up now, and it's so important that it deserves its own name. Whenever we have a linear system whose constant term is the vector 0, then a linear system like that is called homogeneous. Homogeneous linear systems just have this 0 vector here. They have one particular feature, which is that they're never inconsistent. Because to be inconsistent, you need a row in your reduced row echelon form of the augmented matrix that has zeros in the first few entries, and then a non-zero entry in the last one. But if you start with a vector of constant that only has zeros, this can never happen. An alternative way of thinking about this is that whenever you have a linear system AX equals 0, there always exists at least one solution, which is the dumb one, the one in which you plug in 0 for x and you multiply everything by 0. So that's always going to be a solution. Homogeneous linear systems are always consistent. They're never inconsistent. Okay, let's finish up this segment with an example. Here's a set of 4 vectors in R3. We'll check that it's linearly dependent. More than that, we want to investigate the relation between the solutions of AX equals 0 and the ways to write the 0 vector. There has been a foreshadowing of this in one of the previous examples, but we'll spend a little bit more time on this example now. Okay, so to check that it's linearly independent, our best method so far is that of trying to look at the associated homogeneous linear system, the system AX equals 0, where A is a matrix whose columns are the vectors of S, and now we want to row reduce it. Let's do some Gaussian elimination as usual. We have 1, 1, 1, 1, 0. Then I subtract twice the first to the second, and I subtract the first from the third. Okay, let's clean this up. 1, 1, 1, 1, 0. The second row, I can multiply everything by -1/2 or divide everything by -2. And the last row, I'll divide everything by 2, so that I get a 1 in that entry. We're almost done. To get to the reduced row echelon form, we just need to eliminate the one above the second pivot. And by doing that, and we do that by subtracting the second row from the first. Zero, 0, 0, 0, 1, 0. Okay, let's look at the pivots here. There's 3. However, there is one column that is not a pivot column in A, which means that this homogeneous linear system has a free variable. And in this particular case, the free variable is x3, which means that the set S is linearly dependent. Okay, we've done part 1 of this problem. We showed that it is linearly dependent. Now let's have a look at the set of solutions of AX equals B. Sorry, AX equals 0. So the solutions here are as follows. By just reading the rows of the reduced row echelon form, we have that x1 has to be -2x3. Oh, we're not done. The reduced echelon form requires me to take the third row and eliminate the one that is up here. But the third row only has zeros, so I will do that right here. And replace this one with a 0. Okay, now we're done. Now this is in reduced row echelon form. And it reads like this. x2 is equal to plus x3, and x4 is equal to 0. When we wrote this as the general solution for this problem, this is equal to saying that all of the solutions are multiples of x3, with a -2 for the first variable, a 1 for the second, a 1 for x3 itself, and a 0 for x4. In other words, all solutions to AX equals 0 look like this. But now let's try to, again, see what happens when we want to write 0 as a linear combination of columns of A. We can just do that by plugging in the solution we found, x3 times -2, 1, 1, 0. When we do this, we get x3 times, go down here. We have -2 times the first column of A, 1, 2, 1, plus 1 times the second column of A, which is 1, 0, 1, plus 1 times the third column of A, 1, 4, 1, plus 0 times the fourth column of A, 1, 2, 3. Now, if you compute this, you'll see that this is exactly the 0 vector. In other words, and it's multiplied by the constant x3, which is just a free variable. In other words, what is happening is that the vector who is a solution for the homogeneous linear system, as its entries, the coefficients you need to write 0 as a linear combination. We'll say more about this in the next video, and I'll see you then.